Hello everyone. In our previous video about enzyme-linked immunoabsorbent assays, or ELISA, you have learned about the fundamentals of ELISA, its various types, and how it has revolutionized diagnostic testing by providing a highly sensitive method for detecting specific antigens or antibodies. Today, we're going to dive deeper and focus on the reverse or sandwich ELISA. This method has shown exceptional promise in the realm of diagnostics, particularly in detecting viral antigens. By the end of this video, you'll gain an in-depth understanding of reverse ELISA and its critical role in diagnosing diseases, especially in the context of the ongoing battle against COVID-19. Okay, let's start. Before we dive into our main topic, let's first review what sandwich ELISA is and what types of ELISAs there are. The sandwich ELISA is an immunoassay that detects antigen between two layers of antibodies, primary and secondary. It begins with a capture antibody specific to the target antigen, immobilized on a solid surface. The sample containing the antigen is added, allowing the antigen to bind to the capture antibody. Then, a detection antibody is added, which binds to the antigen, forming a sandwich structure: capture antibody, antigen, detection antibody. There are four primary types of ELISA: direct, indirect, competitive, and sandwich or reverse ELISA. Each method has its unique attributes and applications, with some overlap. Sandwich ELISA surpasses other methods in terms of sensitivity and specificity due to its unique sandwich format. Particularly advantageous in detecting antigens with multiple epitopes, the technique relies on monoclonal antibodies for precise detection and polyclonal antibodies for effective antigen capture, offering superior versatility. Sandwich ELISA is named as such because it involves the antigen being sandwiched between two antibodies, a capture antibody and a detection antibody. It is a highly sensitive and specific method because it employs two antibodies that bind to two distinct epitopes on the antigen. The term reverse ELISA is occasionally used to describe a sandwich ELISA where the detection method is reversed. In a traditional sandwich ELISA, the plate is coated with the capture antibody and the detection antibody is conjugated to an enzyme. However, in a reverse setting, the plate could be coated with the antigen and the capture antibody could be the enzyme conjugated. To clarify, reverse ELISA is not a different form of ELISA compared to sandwich ELISA, but is rather a modification of the traditional sandwich ELISA. It still utilizes the same sandwiching principle, but the roles of the antigen and antibody are switched. Alright, let's take a look for SARS-CoV-2 how ELISA is super handy for detecting either the presence of viral antigens indicating an active infection or the presence of specific antibodies against the virus, indicating a previous or ongoing immune response. IgM and IgG antibodies are two main types of immunoglobulins, or Ig, produced by the human immune system. In detecting pathogens such as SARS-CoV-2, the presence of IgM and IgG antibodies can help determine the stage of infection and immune status. For example, the presence of IgM antibodies may indicate that the patient is in the early stage of the infection, while the presence of IgG antibodies may suggest that the patient has already developed an immune response to the pathogen. Now let's go through the steps of a reverse ELISA to detect SARS-CoV-2 using viral antigens or IgM and or IgG antibodies. So first things first, we need to coat the microplate with either the viral antigen like the spike protein or nucleocapsid protein, or with specific antibodies against SARS-CoV-2. This step helps us capture the target from the patient sample later on. Now, after coating the plate, we need to block any unoccupied binding sites with a protein solution. This step is essential because it helps us avoid non-specific binding that might affect our results. Next, we add the patient sample to the plate. If we're detecting viral antigens, we'll use samples such as nasal pharyngeal swab, while if we're detecting IgM and or IgG antibodies, we'll use blood serum or plasma. During this step, the target molecules in the sample will bind to the immobilized antigen or antibody depending on our focus. After the patient's sample has had time to bind, we wash away any unbound material. Washing is crucial because it reduces background signal and ensures that only the target molecules remain attached to the plate. Now we introduce detection antibodies to the plate. If we're detecting viral antigens, we'll use enzyme-conjugated antibodies specific to the SARS-CoV-2 antigen. If we're detecting IgM and/or IgG antibodies, we'll use enzyme-conjugated secondary antibodies that are specific to human IgM or IgG. It binds to a different epitope on the captured antigen, forming a sandwich with the target antigen in the middle. Once the detection antibodies have had time to bind, we perform another wash. This step removes any unbound detection antibodies and helps us to further reduce background signal. Next, we add a substrate that reacts with the enzyme on the detection antibodies. When the enzyme cleaves the substrate, a color change occurs, and the intensity of this color change is proportional to the amount of target molecule, either the viral antigen or SARS-CoV-2 specific IgM and/or IgG antibodies present in the sample. Finally, we measure the optical density of the color change, typically using a microplate reader. This measurement helps us quantify the amount of the target molecule in the patient's sample, which can be used to assess whether the patient has an active infection or has developed an immune response to SARS-CoV-2. And that's it. Those are the main steps of a reverse ELISA to detect SARS-CoV-2 using viral antigens or IgM and/or IgG antibodies. What are the advantages of the reverse ELISA test? The reverse ELISA method utilizes an antigen for capturing antibodies, which allows a more specific detection and assessment of the immune response. This approach is well suited for complex samples as it doesn't necessitate antibody purification prior to testing. Compared to traditional ELISA tests, reverse ELISA provides enhanced sensitivity, often 2 to 5 times that of direct or indirect ELISA, which enables prompt and accurate detection of antibodies in an unknown sample. Moreover, this technique embodies a high degree of flexibility due to its capacity to detect various antibodies, thus broadening the scope of immune response analysis. Remember, while reverse ELISA has these advantages, it also requires careful sample handling and rigorous protocol adherence to avoid false positives or negatives. It's important to interpret the results in the context of other clinical and diagnostic information. Thank you for watching.